least one multiple choice question and probably one free response question on something of this nature, I would be surprised. Sometimes it'll be like a naked problem with no context. Sometimes it will be, you know, like I know there was one a while back about a squirrel on a straight clothesline or something that kept going back and forth, which was basically this type of problem. So they typically put this on the exam. So what we'll be looking at here is position, velocity, and acceleration and how those relate to each other. And this is huge in physics. So if you find yourself taking a physics class, whenever you take physics, there is a option for like an algebra-based physics, or you can take calculus-based physics. I never had the algebra-based physics. I had the calculus-based in college. Last year, sometimes Braden and Connor would come ask me questions on their algebra-based physics, and calculus just makes it make so much more sense than what they were doing, because they had like a page and a half of like crazy formulas that nothing was defined on, that I could never figure out what to do. But I could do it from the calculus perspective. So our position, velocity, and acceleration are going to be related. One thing that you have probably done before, did Miss Ball do the pumpkin chunking with you guys, where she didn't have you guys make catapults and stuff? I always do that in Math 1. We make catapults, we go shoot them, we look at like the projectile motion of that. So like one thing that this definitely applies to, and I'm going to use that for this graph, is like anytime you have projectile motion. So if you throw something into the air, if you're ignoring air resistance, which, you know, on Earth we can't actually ignore air resistance, but if you have a fairly dense object, it's going to be close. Now, if you throw a tissue into the air, it's not going to follow projectile motion. But if I just take something like my remote and throw it into the air, it's going to be pretty close there. So, you know, from whatever height you're at, when you throw something into the air, it's going to follow a quadratic projectile motion that'll look like this. And so on this graph, your x-axis would be some sort of time. I think the one you're most likely to see is seconds, so let's just use seconds, but it could be anything. It could be minutes, it could be hours, it could be days. The equation changes based upon which one you have. And then your x-axis would be your position. Specifically for this, it would be height. It would be how high that object is. But sometimes that will be measured in, sometimes that might not be height. That might be the distance you've traveled, like left and right. It can depend. But we'll just go with height for this one since we're looking at that scenario. And I'm going to go with meters there just to give an example of what you're looking at, right? Your position graph is typically going to be given, it depends on the question. A lot of times they'll call it S of t or X of t. And the units for your position graph is just going to be your unit of measure, which in this particular case is going to be meters. But again, it could be feet, it could be miles, it could be any of, any length measurement for that. Now, if we take the derivative of this, so if we are taking the derivative of this graph, let's talk about units. So as we take the derivative, the x-axis stays the same. We would still have time right here. It would be seconds. But as we take the derivative of this, our units for this, so if we've got S prime of t, or x prime, whatever they've called it. They sometimes use a different letter, but s and x are the ones I see the most often. If we have s prime of t, the units now would be change in y over change in x, so height over time, which for this particular example would be meters per second. What is measured in meters per second? It is not a distance. What would we call it? It's on the page there. Velocity. That is your velocity. So s prime of t is equal to, a lot of times we'll call that v of t. So if we take the derivative of velocity, we're going to get position. Take the derivative of position, we get velocity. Now, that, if we think about what that's going to look like, in this particular case, my graph is increasing here. It is decreasing after that point. So I would have a positive velocity, then a negative velocity. It's going to look, that graph is going to look something like this. This graph is a quadratic, so the derivative of a quadratic would be a line. What does it mean to have negative velocity in this particular case? It does not mean it's slowing down. It means your height is decreasing, right? So if you have, on the way up, you're going to have positive velocity. On the way down, your velocity would be negative. We think most of the time in terms of speed, right? Slowing up, speeding down. Or slowing down, speeding up is what we typically think of, right? We don't think about direction. So like when you go home from Elkin High School and you drive to your house, you look at your speedometer, it tells you that you're going 55 miles an hour, or in some of your cases, it tells you going 95 miles per hour, and the cops pull you over. That is your speed. It does not take into consideration your direction at all. But in the case where we're looking at this on a graph, if you think of tangent lines right here, you know, your tangent line right here is positive. That tells us we're on our way up. Our tangent line over here is going to be negative. That tells us we're on our way down. So when we're looking at graph scenarios, we're going to be looking at velocity, which does have a sign. Then we can think about, let's see, let me put my units over here. We got meters per second. So if I take the derivative again, I would have s double prime of t, or I could call it v prime of t, or this is going to give us our acceleration right here. So the units for this, here, this graph would have time on the x-axis still, which would be s, and then whenever I'm finding the units for this, I would do change in y over change in x, which would be meters per second divided by seconds. So that would be meters per second, or I could call that meters per second squared, depending on which one you want. Now, the slope of this graph right here would be negative, right? So I would be looking at just having a acceleration that's going to be like a straight line, and it would be negative. This would be our A, T. Let me label this one. B. Let's see. Why is acceleration negative in this case? Your velocity is decreasing. Why is your velocity decreasing? If you think about what's happening, if you take something and throw it into the air, why is velocity decreasing? what is causing this velocity to decrease? Gravity. This would be your acceleration due to gravity, and it is negative because it's pulling the object back towards the earth, right? So even as whatever you throw into the air is on its way up, it's still going up, but it's slowing down, right? Your velocity is still positive here, but it's not as positive as it was in the beginning. It slows down until it stops up here. Then it starts falling slowly at first, but faster towards the end. So you might have a velocity of 50 at the beginning, and then it might be 20, 10, 5, 2, 0, and then it starts to -2, -5, -10, -50 on its way back down. So that acceleration is negative for that. Okay, questions? Yes? In that case, you would probably be looking at like horizontal motion. So if you think about a car accelerating, like what typically happens with a car is you would like start off increasing your speed a lot at first, and then it kind of slowing down. Like it takes a lot longer to go from 60 to 100 than it does from 0 to 60. So what you would see here, this would be like your distance that you have traveled. So you would see your velocity would always be your velocity would be increasing the whole time, but your acceleration for that, since this would be, I think it was right, since you are increasing, but your acceleration would be decreasing. You're still it'd still be positive because you're still accelerating, but you're getting faster and faster. But it would be a decreasing line above the x-axis for that. So we'll think some more. That's a good question. We'll think more, but you would measure that more on like a horizontal scale, because it would not apply to this like parabolic motion for that. Okay, so this is what I would just call a naked problem. All right, they like to give these like weird problems where we just have this hypothetical object moving along a straight horizontal line. Sometimes it'll call that line the x-axis, so that at any time t from 0 to 9, its position is given by this equation, right? So this equation gives us the position of the function. So A asks for what is the velocity of the particle at t equals 5. Is it moving to the left or the right? So derivative of x is velocity. Whenever you do these problems, you want to do this. You want to say x prime of t. Now you can get away with just calling this x prime of t the whole time, but I like to say that this equals v of t and use that v for velocity so that it's very clear to me that this is velocity. You need to write both of these things because you're showing that you're taking the derivative of the original and you know that that is the velocity. And then we just take the derivative of this. Let's see, Kayla, what do we get when we take that derivative? Good, 2t minus 3, or you could do -3 plus 2t, either one, perfect. Okay, and they want to know particularly at 5. So, Abby, what would we do to find that velocity at 5? Very good. So, we'll have v of 5, make sure you label it, would equal 2 times 5 minus 3. So, we've got 10 minus 3 equals 7. All right, and so, velocity at 5, and this one doesn't give us any units. This is a naked problem, so it's 7 units per time, but we don't know what they are, so we don't have to tell what the units are for this problem. 7 is our answer. The question also asks us this particle moving to the left or to the right. Which direction would be positive whenever we're looking at a horizontal line? we're looking at the right. So since our velocity is positive, the particle would be moving to the right. So since v of 5 is positive or is greater than 0, the particle is moving to the right. Okay?
So would v of 0 be negative 10?
V of 0 would be, yes, it would be negative. You get negative 3 for that. So at 0, you'd be going to the left. Okay. All right, B says, what is the acceleration of the particle at t equals 5? Is the particle speeding up or slowing down? Okay, and we'll talk about this. This is kind of crazy here in a second. But the acceleration of the particle, if I want acceleration, what do I have to do? Second derivative. So since I've already called this v of t here, I could just do v prime of t. And I like to go ahead and call it a of t for acceleration. You even could do x double prime of t over here if you want, but that's not necessary. But you do need to show v prime of t equals a of t. And let's see, Miles, what do we get when we take the derivative? It's just 2, right? So if I want to plug in 5 of this, what am I going to get? Just 2. There's nothing to plug in there, so it wouldn't matter what number I plugged in, my acceleration is 2. So, the acceleration is 2. Are we speeding up or slowing down? We're speeding up. Now, do I have another problem on this? Let me look ahead. The particle is speeding up. Okay, since that derivative is positive, it tells us that the velocity is increasing, right? And since that velocity was 7, that means that, our velocity is going up. At this point, it's going up 2 units per unit of time. So right here at 5, it would be 7. If it continues on that path, it'd be, 9 and then 11 if it was a constant. Which is going to be because your acceleration is always constant there. So the particle would be speeding up. However, let me see if I've got another problem on this. I need to explain this now. I think I do. Oh, yeah. Okay. Now, here is the crazy thing, though. What we want to think of is that if our acceleration is positive, then we're speeding up, right? If our acceleration is negative, we're slowing down. That is true if your velocity is positive. If your velocity is negative, it is not true. Because speed does not include direction for that. So let's just think of a couple scenarios here that I need to explain this here. So like what we're looking at right now is we are looking at, we have our time and our velocity, right? And so at 5, our velocity was 7. And the acceleration is 2. So we would be like at 6, our velocity would now be 9. And at 7, our velocity would be 11. And at 8, our velocity would be 13, right? And since the acceleration is just a constant number for this, that would actually be the case of what is happening. So our velocity here is increasing, right? So this is the case where we have positive acceleration, positive velocity. All right. Now let's think about negative acceleration. That's not for this case, but we've got negative acceleration, negative velocity, and positive velocity. So let's think about the same scenario. We're at 5. We got a velocity of 7. Now, if acceleration was like negative 2, right, then what would my velocity at 6 be? It would be 5. And then at 7, I would have 3. And at 8, I would have 1. Right? So this is definitely speeding up. And this is slowing down. To me, this is easy to think about. If you are going in the positive direction, positive acceleration, or positive velocity. If your acceleration is positive, you're speeding up. If your acceleration is negative, you're slowing down. Makes sense. Now, let's think about the crazy situation that somehow I have a hard time picturing like this in my head. All right, so let's say that we've got this case. Our velocity is no longer 7, it's negative 7. So it's the same speed, right, as we have in our other tables. The speed is the same, but you're going the other direction. So this is like in the action movie where they flip the car around, now they're driving backwards, right, which is always really realistic. I'm sure people can actually do that. So they are, this is going same speed, opposite direction. So this time, let's do positive acceleration, negative velocity. All right, so if my acceleration is positive 2, what would my velocity be at 6? Negative 5. What about 7? Negative 3. 8 would be negative 1. Velocity has a sign. Speed does not. What's your speed? Right here. 7, 5, 3, 1. Speed is your absolute value. Are you speeding up or slowing down? Slowing down. So your acceleration is positive here, but you're actually slowing down. Right? Yes. Yes. Yes, so the sign of your velocity tells you the direction. But velocity is speed with a direction, is what it is. So whenever we're talking about speed, we don't care about that sign. So acceleration makes this increase numerically, which means we're going from negative 7 to negative 5 to negative 3, which are bigger numbers. But speed is actually decreasing there, because if we did speed, we would have absolute value on that. So you would be slowing down if you had negative velocity, positive acceleration. If they're both negative, that's the last case we need to think about. So we've got time and velocity. Let's do same thing. 5, negative 7. This is negative acceleration, negative velocity. Right? So if we have an acceleration of negative 2, what would my velocity be at 6? Negative 9. And 7 would be negative 11. And 8 would be negative 13. So, for velocity, my velocity is decreasing. The value of my velocity is decreasing. But when I'm talking about speed, I don't care about that negative sign. I only care about the absolute value of that velocity. Am I speeding up or slowing down here? Speeding up. Okay, so on speed questions, and I realize I've not given you enough room to write much of this at all, but on speed questions, if it's talking about velocity, you answer it differently. But if it is a speed question, If acceleration and velocity have the same sign, you're speeding up. And if your acceleration and velocity have different signs, you're slowing down. So, in order to answer a speed question, you have to check velocity and acceleration. What students do incorrectly most of the time is they just look at acceleration, and if acceleration is positive, they say that you're speeding up. And if acceleration is negative, they say you're slowing down. Which is fine as long as your velocity was positive in the first place, which is what we normally think of. But you have to check both for that. They also like to put those on there. Okay, questions on that? All right. Okay, this one we are going to definitely use our calculators for. And let's see. I have a new, oh, good gracious, what all have I got open over here? I have a new trick. Okay. Let's see. Why do I have so many things open? Okay, let's go over here. This is what I need. And I haven't done attendance. Good gracious. Starting the new year off right here today. Let's see. Where is this at? I saved it the other day. Why is it gone? Oh, there it is. Okay. All right, I got me a new calculator simulator here. Why is it doing that? Okay. That hopefully will be easier to see than when I have to do that. If you're ever somewhere without your TI-89, but if you're a good nerd, you won't leave home without it. But TI-89simulator.com is what I'm using here. So you could look that up. So let's go to y equals, let's type this in. Everybody grab your calculator. Does that show up? It's still kind of small, but I can actually make this a little bigger. Okay, so this time we've got an equation moving, a particle moving along a straight line at time t. A says find the time or times from 0 to 20 at which the particle is at rest. What are we going to need to know if the particle is at rest? At rest would mean it's not moving. Any ideas? We're looking for zeros of what? Velocity. Because if the particle is not moving, the velocity is going to be 0. Position could be something else, right? Position being 0 would mean we're like at the origin point. But velocity being 0 means the particle is at rest. So if you see that phrase right there, and you probably will, some particle at rest, that means v of x equals 0. So, for this equation, we need to know the derivative, which since this is a calculator active question, let's just go here and differentiate y1 of x I think it should be able to do it. And we have a couple options here. I don't know which one would be best to do. We can either try to solve this using the solve feature, or we can graph this and look for the zeros. Let's try solve just to see if it works. So if I do F2 solve, I'm going to go up here and grab this, say that it equals 0, and do comma x. So I did solve. I went up there and just hit enter on that so that it put that there, put equals 0, comma x. Let's see if it works. It did. And it gives us two answers, and they are both between 0 and 20. So that worked pretty well. If that doesn't work or gives you crazy answers for that, you can graph it and look for the zeros there. Okay, so we have, we would say the particle is at rest. When x equals 0.021 and x equals 10.639, because f prime of x equals 0 at those points. And I called it f prime of 0 instead of calling it v of x, f prime of x instead of calling it v of x. You could do either one, but because the original function is f, if you change it to v, you need to state that f prime of x equals v of x. Right there. So if you want to use v instead of f prime, you need to state that the derivative of f is v. Okay, questions there? All right, B says, what is the position of the particle at x equals 0? How do I find that? If it's asking for position, which equation? It's not the 0 of the first graph, because 0 would mean like the x-intercept. You don't have to use a such that. It is just when your x equals 0. All you're finding for this is you're plugging in 0 to this. So you would do f of 0, which on here we can just do y1 of 0. You're just plugging in 0 into that equation, and you will get 6. So if it is asking you for a position at a specific time, you just plug that number into the position formula. It's not saying when is the position 0. If it said when is the position 0, then you would look for the zeros on the graph for that. But this is asking, this is like the time is 0, what is the position? So we plug that in. Does that make sense, the difference in those two things? All right, so the position at 20, Lucian, what should we do for that?
Should we just
Plug it in again. So we'll do f of 20, and if we do y1 of 20, we will get, oh gosh, let's hit the green button before we hit enter on that one. 12.544. If we we round that to 3 places. Or keep the whole decimal. Either is fine. Okay, so we got this information. D says, what is the total distance that the particle traveled on the interval from 0 to 20? What do you guys think? No, but that's what it feels like we should do, right? So if we do 12.544 minus 6, what you're finding is displacement, how far you are from your starting point. So I like to use this example. Luke just went to the bathroom. So let's pretend that Luke went to the bathroom and he was going to go to this bathroom over here. But he went to this bathroom and they were cleaning it, right? So he couldn't use that bathroom. So then he had to go back down to the bathroom next to Coach Wood's room, right? So let's say it took him 20 seconds to do that, right? So he started here at my room. He went back over to that bathroom. Then he ended up back over here at this bathroom, right? So his displacement is the distance from my room to the bathroom that he is currently at, right? That is his displacement. That would be the 12.544 minus the 6. Is that the total distance that he walked? No, because he went further than that, right? He backtracked on this. So this problem is to show you that there's a big difference between displacement and total distance traveled. And the reason the total distance traveled is different is because was this particle always moving in the same direction? I don't know, right? We probably not, because the particle, the derivative was 0 twice. Now, it could have been still positive. It could have bounced back up. But to know more about this, we really need to look at the derivative of this function. So that's one. So let's go. Do you guys know how to copy and paste on these calculators? If you go back up to where you found that derivative for this. So if you go back up to where you found that derivative, and you do green button, copy. Right there, it's that up arrow right here. So you do green button, that up arrow. Then you can go to y equals, and we really, well, I'm going to put it in y2, and we do green button, paste. Here. Now, when I graph this, I really only want to see that second one. Right now, I'm interested in what that graph looks like. So I don't want it to graph both of these here. So notice that they both have check marks next to them right now. If you see F4 says check mark, so if you go up to that top one and do F4, it'll take away that check mark. So it'll still be in your y equals, so you can use it later if you need to, but it won't graph it. Okay, so are we good here? Do I need to troubleshoot anything before we graph these? Looks like it's, I'm sure it probably quits going at some point, but it looks pretty infinite. More than you would ever need, I'm pretty sure, Troy. Stops at 99? Okay. 99, Troy. All right. So if we graph this, oh, actually, before we graph it, what do we want our window to be? 0 to 20. Let's go to window. Oh, wait. Window. Let's go 0, 20. And then after we get the x right, what do we want to do so the y's show up correctly? Zoom, which one? Fit. Zoom, fit. If we do that first, it'll graph it quicker. If we had just graphed in standard view, we'd probably have to do this again. Now, I will say that this graph is slightly misleading because the particle is at rest at 0.021 and 10.539. So it is actually going to hit the x-axis there. I'm going to go over here and I'm going to go to my window. I'm going to make that a negative 1 right there. And graph so we can see. You really can't see it. I think there's an asymptote right there. That's one reason the solve feature is good on this. I think what's happening is it's like getting really, really steep right there because it should actually cross the x-axis right after 0 right there. So our particle from, I think we have a positive velocity from 0 to 0.021. You can barely see it on the graph there. I think I made up this problem. It'd probably be better if they had made it and it wouldn't do this right here that's misleading. And then which direction are you going all the way up to 10.639? If our derivative, we're looking at derivative, if it is below the x-axis, derivative is negative, so we're going to the left here. Then we go to the right. So when that derivative is below the x-axis, your particle is going to the left, and when it's above the x-axis, you're going to the right. So what we need to do here is, what happened is, Luke, we've been using you as an example here in your absence. So we said that our example here, we found like where this particle was at 0 and at 20. And the difference in that was like 6.544. We could just subtract those. That would be displacement. But we used the example that maybe you left this room and you walked down to this bathroom and they were cleaning it and you couldn't use that bathroom. And so then you had to walk back to the bathroom next to Coach Wood's room. And you were in that bathroom. Yeah, you might not have made it. So glad this didn't happen to you. But if you did that, your displacement would be from my room to where you're at right now. That would be what we would get if we subtracted these two things. But the total distance that you traveled would be further because you went that way first and then had to go this way. So that's what's happening in this particular case. So what happened here, if we're using Luke going to the bathroom here, we have him go out the door. That's where we'll have him start. And he maybe like almost decided to go this way, just a little tiny bit, right? So, we know f of 0 was 6. Then we need to know his position at 0.021. So if we do y, this is one reason I don't like to take y1 out of the y equals, because I want to do this, y1 of 0.021. I get 6.07194. So Luke goes out of the door. He takes just a step, a fraction of a step in this direction, but changes his mind and decides to go this way to this bathroom. So if I do f of 10.6, what was it, 10.639? If I do y1 of 10.639, I'm going to get negative 11.4609. So that's his position. I guess the x-axis might be right there at the crossroads, and then he goes, or the origin's right there at the crossroads. He goes further past that. So he goes all that direction. Then he realizes that the bathroom is closed. So he has to go all the way to the other bathroom. And we've already found f of 20. It was 12.544. So if we look at each leg of his journey, right? from 6 to 6.07194, that was just 0.07194 units. Just a tiny hesitation in that direction. But then, this distance right here, if we take that number and subtract 6.07194, we get 17.5328. Right. We do not include the negative because we were talking about distance traveled, which is going to always be positive for that. So your distance traveled is going to always be positive. Then we need to know the distance between these two. So if we take our 12.544 and subtract the negative 11.4609, then we get 24.49. For that. So he made like a hesitation step in this direction. He went 17 feet to this bathroom, and it took him like 10 seconds to do that. Then he made it all the way back to this bathroom. He's in more of a hurry now. In the 9 seconds, he went to 24 feet back to the other bathroom. Right? So if I want to know total distance that he traveled, I would add all of that together. So I would take those numbers, add them together, and add the zeros. And that would give me 41.6096. Whatever units we're using here, feet, whatever. So his displacement would have only been like 6.5, but his actual distance traveled was 41.609, since he made a bad decision on which way to go at the first, right? Yeah. Yeah, he was messing me up there. All right, so does that make sense, the difference in displacement and total distance traveled and why we have to look at those different? If you get displacement, it's a much easier problem. You just have to subtract how far you were. But they love to ask total distance, obviously, because it is a harder question where you have to look at what's happening there. And velocity. A particle is traveling on the x-axis, has the position x of t at time t. The graph of the particle's velocity is shown from 0 to 5. Which of the following expressions gives the total distance traveled by the particle from 0 to 5? And that, I copied this. It says which of the following. It should say right. Let me fix that. Right and expression. All right, so x of t is position. If I do x of 0, that gives me position at t equals 0. And if I do x of 5, that gives me position at t equals 5. If I do x of 5 minus x of 0, what is that going to give me? Is that going to give me total distance? Probably not. Not in this situation. This gives me displacement. Okay. Now, sometimes displacement is the same as total distance traveled. If Luke leaves this room and walks straight to the open bathroom, his displacement and his total distance traveled are the same, right? Because he went in one direction, right there. However, is this particle going in the same direction the whole time? It is not, because velocity is positive here, and then it's negative here. So since our velocity is positive over here, particle is moving to the right, or the positive direction, whatever that is. And then over here, we're moving to the left. So we have to split this up right here at 2. Right? 2 is where we switch directions. So you have to think about signs on this. If I want to know how far he went, he was going to the right here. Which one's going to be bigger, x of 0 or x of 2? If right is our positive direction. X of 2 is bigger. So for this leg of the journey, I would need to do x of 2 minus x of 0. If I don't do it that way, I'm going to get a negative number. So I'm going to put some brackets around that. Now, I need to add the distance from 2 to 5. Which one is bigger, x of 2 or x of 5? X of 2. So for this one, I need to do x of 2 minus x of 5. I think they leave it like this on the answer choices on the one you're going to actually see. There's a chance they could combine those x of 2's there and have like 2x of 2, but I don't think they do that for that. So the order has to be different because you have to think about which one's bigger. All right, we're out of time.